Oye, perdón, una pregunta. ¿Va a ser lo hago en inglés o en español?
En inglés.
Ok, sí,
Okay.
muy bien.
Okay. Hi, everyone. Thank you for attending this new Saphir webinar. On this occasion, we have the honor of receiving Professor Pedro Ochoa from University of California as a speaker. Pedro was recently professor here in Chile at PUC. He is currently a senior researcher of Saphir, so he's one of us. He participated in several experimental collaboration, among which is Juno, Atlas, and Dune, right? Today he will tell us about the physics with reactor neutrinos, current status, and prospects. So thank you for your time, Pedro, and please go ahead.
Yeah, thank you so much for the invitation. It's really a pleasure to be here with all of you and get this chance to tell you a little bit about my work. So this is a photo of the far side of the Diabay reactor neutrino experiment. Is one of the experiments we're going to be talking about. And here below, I just put a couple of logos, some of the institutions that I work with. And as was already highlighted by Juan Carlos, Saphir is definitely one of them. And I will also mention later where exactly Saphir is involved in all of this. So this is the plan for today's talk. I'm going to begin with a short introduction for, first of all, neutrinos, because remember, this is a talk about reactor neutrinos. So first of all, why do we care about neutrinos? Then I'm going to discuss the basic principles behind reactor neutrino experiments, how they work in general. We're going to introduce some important terminology and some important concepts. Then, and this is going to be the center of the talk, or the meatiest part of the talk, I'm going to give you a couple of highlights of what's been happening in this field. So I'm going to discuss some recent experiments, Diabay being one of them. I'm going to show you a couple of results, both for oscillation neutrino physics and as well as comparing what comes out of a nuclear reactor with what we expected should come out of a nuclear reactor and the lessons that we draw from all those comparisons. Then I'm going to briefly discuss the future, what's in the future for this field, and then I'll just summarize and conclude. And a disclaimer that I think something that I think will be obvious as we go through this is that I'm a collaborator both in Diabay and in Juno. And so I'm going to be highlighting those experiments more than you would normally hear in a talk like this. Okay, so let me begin with an introduction to neutrinos. Why do we care about neutrinos? And I believe if we want to understand our universe, we need to understand neutrinos. And there is at least 3 reasons why this is the case, 3 reasons in my mind. The first one is that neutrinos are an excellent tool to understand many different sources of neutrinos, both in the Earth, our planet, for example, nuclear reactors, the Earth itself, etc., and outside of the Earth, so supernova stars, the sun itself, cosmic rays, etc., because neutrinos give us complementary information to what we can gain with other sources, for example, photons in the case of some of these astronomical sources. So that's number 1. Number 2, even though they're tiny in terms of their mass, they're actually pretty important in the big scheme of things. They do shape our universe. For example, neutrinos do play a role in the large-scale formation of our universe. It could also be, for example, that neutrinos hold the key as to why there is this matter-antimatter asymmetry in the universe, etc. And finally, number 3 is that neutrinos are an excellent window to new physics. And what I mean here is not just that neutrinos are good probes to look for new physics. I think that's certainly true, but it's even deeper than that. Neutrinos are already new physics because they behave in a way that goes against how we expect the neutrinos to behave. And to be specific, I'm talking about neutrino oscillations. So neutrino oscillations implies that neutrinos are massive, and that goes against how the architects of the Standard Model built the Standard Model. They assumed that neutrinos were not massive. And so let me just explain very briefly neutrino oscillations, because it's something that we're going to be talking about a lot today. So just as a reminder, first of all, neutrino oscillations means that if you begin with a beam of neutrinos of one flavor, here represented by the cars, and you let this beam propagate, and then you sample the composition of this beam some distance / time after, then you will find that some of these neutrinos change to another flavor. And then if you repeat this process for a bigger distance, then you might see the third flavor appearing. In this analogy, for example, the cars could be muon neutrinos, the vans could be tau neutrinos, and the buses would be electron neutrinos. This is actually what happens in an accelerator experiment like DOOM. Now, why does this happen? Really, it's quantum mechanics in its maximum splendor and observable over macroscopic scales, which always blows my mind. So what happens here is that the states in which neutrinos interact, namely nu e, electron neutrino, muon neutrino, tau neutrino, they do not correspond one-to-one with the neutrinos that have definite mass. The neutrinos that we call mass eigenstates. These ones we just call nu1, nu2, and nu3. Rather, they're mixtures of each other as represented by this pictorial photograph. Now, the matrix that tells us how this mixing occurs is called PMNS. I'm not going to show you the whole thing. I think the most important thing to remember here is that this matrix is parametrized in terms of 4 parameters. So there's 3 mixing angles because basically it's a rotation. So you need 3 angles. We call them theta 1, 2, theta 1, 3, theta 2, 3. And then there's one phase that if it's non-zero, it means that neutrinos violate CP, the charge parity symmetry. So this would be, of course, huge news. We don't yet know if this is the case. I will emphasize this in the next slide. So with this framework, with this mixing framework, as well as some basic assumptions, namely that neutrinos propagate as plane waves, I can predict if I start with a beam of a certain type. Again, let's imagine these are now electron antineutrinos. What's the probability that they will continue to be electron antineutrinos after propagating for some distance L if these neutrinos have some energy E? And so you can calculate these probabilities, and this is just a rough example. It's not an exact expression, but there's something important to remember about this, which is that the differences in the squares of the masses, which we call the mass splittings, these give us information about the frequency of this phenomenon. In other words, they tell us about how often this phenomenon repeats itself in this L over E space. The mixing angles, they give us information about the magnitude of this effect. So they give us, in other words, information about the amplitude. How much is the, for example, disappearance of neutrinos or appearance of neutrinos that we can expect? Okay. Now, there's been a lot of progress in neutrino physics in the past 2 decades. I remind you that the discovery that neutrinos oscillate came basically at the turn of the millennium, 1998, 2000, 2002 at the most. And it's been 2 decades since then, roughly. And now we know these mixing angles and these delta M squares to better than 5%, which I think is remarkable. Again, it's only been 2 decades. Nonetheless, there's still a lot of questions that we still don't know, whose answer we still don't know. So we know the differences in the squares of the masses, and we know, as I said, to about 5% or better. But we don't know what the absolute mass of neutrinos is. And perhaps even more interestingly, we don't know what the origin of those neutrino masses is. We also don't know how these masses are ordered. Naively, you would think 1 is the lightest, 2 is the middle, and 3 is the heaviest. And this is one possibility that's on the table, but it doesn't necessarily have to be this way. We do know that M2 is heavier than M1. We know this from what is called matter effects in the sun. But we don't know if the third eigenstate, M3, is higher or lower than the 1-2 pair here. And so we refer to these 2 options as the mass ordering or the mass hierarchy. Both terms are used. And this is a big question because its resolution affects a lot of branches of neutrino physics and beyond. For example, it affects whether or not we can expect to detect neutrinoless double beta decay, et cetera. There's many implications. So it's one big question that we're after. There's also one mixing angle here, theta 2,3, that appears to be consistent with 45 degrees. So the question is it 45 degrees? And if so, why? Because maybe that would point to some symmetry that we're not aware of. If it's not 45 degrees, then is sine squared theta 2,3 larger than 0.5 or smaller than 0.5? In other words, what is the octant? We also don't know, and this is a biggie, whether or not there's CP violation in the neutrino sector. This in turn has important cosmological implications. We don't know if neutrinos are their own antiparticles. In other words, if there's a Majorana mass term in there. We don't know if there's more than 3, etc. Okay, so these are some of the questions that we're after, and nuclear reactors can help us address many of these questions. So let me now discuss nuclear reactor experiments in a little bit of detail. So nuclear reactors, here's a mouthful, a list of things. Let me read it. So widely available, flavor pure, cost effective, extremely intense, well understood source of electron antineutrinos. So let me just comment briefly on this. Basically, nuclear reactors are an excellent source of neutrinos. Why? Because first of all, they're widely available. In other words, now you can find nuclear reactors, well, not everywhere, but in many places around the world. Second, they're flavor pure, only electron antineutrinos, and only that flavor is emitted, to very good approximation. You can see this as a pro or as a con, but in general, it's seen as a pro because it means you know exactly the composition of your beam. There's no ambiguity there. Cost effective. Why? Because you don't have to pay, you researcher don't have to pay for the installation, maintenance, and operation of a nuclear reactor, typically, unless it's a research reactor. It's paid for by itself. It's paid by some company that wants to make money by producing electricity. You just got to get their permission to put your detector next to their reactor. It's extremely intense. Nuclear reactors are the most intense. Let me start again. Actually, I was on the right track. They're the most intense man-made source of neutrinos. So a nuclear reactor produces in a minute more neutrinos than you get in an accelerator in a year. The thing or the disadvantage here is that the neutrinos are emitted in all directions, whereas in an accelerator, you can kind of guide them, but they're super intense nonetheless. It's in the order of 10 to the 20 neutrinos per second for a nuclear reactor that's 1 gigawatt of power, thermal power. And finally, well understood. If you know pretty much what isotopes are fissioning in your reactor and what's the power of your reactor, you can predict to a few percent how many electron antineutrinos should be coming out. Now, let me just very quickly come back to this issue of flavor pure, in case you're wondering, why do we even get neutrinos from a nuclear reactor in the first place? And why specifically this type? The reason is actually quite simple. This is what happens in a nuclear reactor, as I think everybody here knows. You have these heavy elements, for example, uranium-235. It gets split into pieces. And since uranium-235, and this is what this graph here illustrates, and other such heavy elements, they have an excess of neutrons over protons. When you break it into pieces, the pieces have a bigger excess of neutrons over protons compared to what they need in order to be stable. And so these products will beta decay in order to fall back into stability. And so it's all these beta decays that give you all these electron antineutrinos. Okay. Now, something that we're going to talk about briefly, it's going to come up a few times, is that there's two types really of nuclear reactors. There's low enriched uranium and highly enriched uranium reactors. So low enriched uranium ones are the most common. These are basically all commercial reactors are low enriched uraniums. These are nuclear reactors that are massive. The typical commercial reactor that is built to provide gigawatts of thermal power. And what's important to remember about these nuclear reactors is that the fissions that occur that give you neutrinos come from mainly 4 isotopes. Is uranium-235, which is black here, plutonium-239. So these two are the most important ones. And then you have uranium-238 and plutonium-241. And the other important thing to remember here is that the percentage of the total amount of fissions that come from each of these reactors, each of these isotopes, in other words, the fission fractions, they're not stable. They change with time. And so what this means really is that if you're looking at the electron antineutrino output of a nuclear reactor, an LEU nuclear reactor is going to fluctuate. Even if there's no refueling, it's going to actually go down, to be specific. And that's normal. It's because of this. So we'll come back to this a little bit later. The other type of reactor that is used for reactor neutrino experiments are HEU fueled reactors. These tend to be research reactors. They're a lot smaller. They're in the order of maximum 100 megawatts of power. And so these are a lot simpler. All of the neutrinos come essentially from the fission of uranium-235. Okay, so this is important to remember. I will remind you of this as we go along. Now, in these kinds of experiments, the way that neutrinos are detected has been, or the primary channel for detection of electron antineutrinos has been this reaction. It's called the inverse beta decay, or IBD reaction. And disclaimer, now a new generation of experiments using a different reaction, the Sevens reaction, is coming online. I am not going to go into that. I'm going to focus on experiments using the IBD reaction today, just because of lack of time. Okay, so in this reaction, the IBD reaction, you have the antineutrino hits a proton, you get a positron and a neutron. And there are many advantages to this reaction, high cross-section compared to other reactions. But perhaps the most important advantage here is that you get two products that are detectable. So the positron is a charged particle, and so everybody here, I think, knows, easy to detect, right? Because it's charged. Typically, we use liquid scintillator, and so it will deposit a lot of energy in the liquid scintillator. We get a lot of light. And then it annihilates, by the way, with an electron that emits 2 gamma rays. We can also see that easily in liquid scintillator or whatever technology you're using. The neutron, it just wanders around until it thermalizes. It stops, basically. And if your detector has an element that likes to eat up neutrons, such as hydrogen or lithium or gadolinium or cadmium, etc., but the most common ones are these three: hydrogen, lithium, gadolinium. Then it's going to get excited, and then it's going to be de-excite by emitting a characteristic gamma ray signal. And so you see both of these signals in succession. You see the positron, and then you see the neutron. You see the tuck tuck. This is what allows us to extract antineutrinos from our data sets. Because for those of you who work in Atlas, you guys are used to imaging, right? The collision, well, not the collision, but everything that comes out of the collision, and you have trucks, and you see, oh, there goes a positron, oh, there goes an electron, there goes a muon, there goes the electron, and then the shower. You can image all of these things. In these experiments, we don't image anything. Everything looks like a point. The positron, we're talking about MeVs of energy, so it just travels for a few centimeters. You cannot see it. You just see flashes of light. And so what really allows us to distinguish antineutrinos from the background is this tuck-tuck, the prompt signal followed by the delayed signal. Okay, and it's a very powerful handle. It allows us to really suppress backgrounds to the few percent level. The spectrum that you get from these kind of experiments is what here is represented in blue. So it looks like this. It's something that peaks around 4 MeVs of energy. And the reason it looks like this is because the spectrum of antineutrinos emitted from a reactor is this thing in black. It's something that decreases kind of exponentially. And then in red, you see the cross-section. And so the product of these two gives you this thing that peaks around 4 MeVs.
Oh, Pedro, can I ask a question? Yeah. Why is it delayed? I mean, it's because of the small mass difference between the proton and the neutron. Is that
why the delay?
Yeah, it's because
the neutron has a little bit of energy, typically tens of keVs, so like 20 keVs or so. And so it won't get captured immediately. It needs to bounce around. Since it's not charged, it doesn't slow so quickly. And so it needs to bounce around a little, finally gets thermalized, and it gets captured.
Okay, so this is going through matter, right? So this is why it's stopped. Okay, but
exactly.
It's not because of the underlying isospin symmetry which forces.
No.
Okay.
No. It's the propagation of the neutron in matter. For example, liquid scintillator or plastic scintillator. Yeah.
So this is order centimeters, meters. This
Correct.
delay?
So no, it would be centimeters. So the distance, typical distance between the prompt and the delayed is in the order of 25 centimeters. I don't remember the exact number, but it's in that order of magnitude, 20 centimeters or so. Yeah.
Okay, thanks.
Sure. Okay, so the other thing I should emphasize is that for neutrino oscillation experiments, we need to know the energy of the incoming neutrino. And we can extract that from the energy of the positron. And this is simply because the neutron is super heavy compared to the positron. So most of the, so it has essentially no kinetic energy. Most of the energy goes to the positron. And that's why if you measure the energy of the positron, you get a proxy for the neutrino energy. That's why you will see many plots that say prompt energy. It's the energy of the positron and its annihilation. It's a proxy for the neutrino energy. Now, what can we do in reactor neutrino experiments? All kinds of things, as I will show you. But one of the main things we can do is neutrino oscillation measurements. And so it's worth me just spending one slide with the basics of oscillation measurements with reactor neutrino experiments. This is the probability of, if you begin with electron antineutrinos, continuing to detect electron antineutrinos. And I'm not going to read the whole thing. Here it is. It's a little chorizo, as we say, at least as I used to say when I was in Chile. But there's a couple of things I can highlight. One of them is that if you look carefully, you will see that 4 out of 6 oscillation parameters appear here, which are these 4. Basically, the 2 mass squares. I say the 2 because there's only 2 independent ones. Once you know the mass ordering, then you know the 2 mass orderings. Then there's 2 mixing angles. The one that's missing is theta 2, 3. And so that means that with this channel, just looking at the disappearance of electron antineutrinos, and just in case we have some students in the audience, disappearance means that your detector is only sensitive to electron antineutrinos. And so if you started with a beam of just electron antineutrinos and they oscillate to another flavor, it looks as if they're disappearing. It's not really that they're disappearing, it's just that they're going to other flavors that you cannot detect. But that's what we call electron antineutrino disappearance. And so it's a powerful tool. You can get access to all these parameters. You don't have to worry about delta CP, which we don't know. This, you can see it as an advantage or as a disadvantage. But if you're interested, for example, in measuring the mass ordering, which is what Dune, Hyper-K, those experiments are doing, it's a plus that it doesn't depend on delta CP, because for those other experiments, it does. And so they have to disentangle the 2 effects at the same time. Here, it's just mass ordering, for example, in the case of Juno. And the other thing I should point out is that depending on what you're interested in here, what parameter, or if it's the mass ordering, whatever you're after, that's what's going to drive your choice of baseline. And so let me illustrate this with theta 1,3. If you're interested in measuring theta 1,3, you want to go to a place, a baseline, where this term, which is modulated by sine squared 2 theta 1,3, dominates, and where this term doesn't play a role, because this involves the so-called solar parameters. So you want to go here, basically, because as you can see, it's all blue and the red is almost nothing. So this is why Diabe, Double Show, Reno, they're here. This is low, small baselines. We're talking about less than 2 kilometers or so. Now, if you're interested in these, in the red, so in the solar parameters, theta 1, 2, delta m squared 2, 1, then you need to go to somewhere around here, and Camland ended up here, for example. If you're interested in measuring everything, which is what Juno is going to try to do, is going to measure all 4, you need to go here. And that's, again, what Juno is going to do. Okay. So depending on where you put your detector, again, you can change. It determines, or let me say it again. Your physics goals determine where you put your detector. If you're looking by the way for sterile oscillations, then you go to the very, very short baselines. We're going to talk about this in a little bit. Now, let me just very briefly say reactor antineutrino experiments have a long history of successes. The discovery of the neutrino itself was done in a reactor neutrino experiment by Reines and Cowan. The Camland experiment made many important contributions to our field. One of them being the fact that they were the first to observe oscillations using terrestrial neutrinos. And this is one of the plots that, most famous plots that have come out of there. I'm not going to go into details, but reactor neutrino experiments had been done since the inception of neutrino physics, or experimental neutrino physics. Now, let me discuss a little bit some of the recent reactor neutrino experiments. First of all, which experiments are they? And then I will show you what results we have gotten from them. So when it comes to current generation reactor experiments, I think we can divide them into two bins, two categories. The first one would be experiments that are designed to measure one specific mixing angle, which is theta 1,3. If you're wondering why would you design a whole experiment to just measure one mixing angle, actually there's a very good reason. It's because this angle was not known until just a few years ago. And we didn't know if it was 0 or not. And if it's 0, then it means we cannot observe CP violation in the neutrino sphere. So there were a lot of implications hanging from this fact. Is it or is it not 0? We need to know. And so the goal of measuring this one angle, specifically answering, is it 0 or is it not 0? Diabase is one of them. We're going to talk a lot about diabase. It has 8 identical, so this is not 8, but here, 8 identical detectors spread out at different distances from 6 nuclear reactors. So this is the most powerful of the 3 experiments, is the one with the most complex configuration also. It has 2 near sites and 1 far site with more detectors there to increase the statistics. There's Double Show. This one was in France, and it used 2 reactors, 2 detectors. And then there's Reno, which used 2 detectors and 6 reactors. Reno is still taking data, but Diabase and Double Show has stopped now, although Diabase and Double Show are still producing results because we're still analyzing our full data set. The strategy here is the following. You want to measure theta 1,3. Remember, let me go back here. We want to measure this. Now, as I will tell you later, we can predict what comes out of a nuclear reactor pretty well, a few percent. That's not enough. If we're going to measure this effect, which is pretty small, it's less than 10%, you see, we cannot have uncertainties in the order of a few percent, or we're dead in the water. So we need to cancel out those uncertainties by doing a relative near to far measurement, because we measure the flux, first of all, and then we compare that, so the flux before oscillations, and then we compare that to the flux after oscillations. And we can cancel all of these detector uncertainties, the detector efficiencies, as well as the uncertainties in the reactor flux. And we can just extract what we're interested in, which is the oscillation probability. So that's why the strategy here is to do this near-far relative comparison. Now, since we're in short baselines, we're less than 2 kilometers. It means we don't need humongous detectors. We need just tens or hundreds of tons. And since we're looking for a small effect, as I mentioned, systematics are everything here. So we need to keep them under control. So these kind of experiments, they use pretty much the same kind of technology. I won't go into the details, but let me just briefly give you an idea of how these work. Basically, the 3 experiments use these 3 zone detectors. So it's like a matrushka or babushka, sorry, I don't remember which is the right term, but the doll inside the doll inside the doll, right? Same thing here. Instead of dolls, it's cylinders. So you have a cylinder inside a cylinder inside a cylinder. And the innermost cylinder is liquid scintillator with gadolinium, because remember, gadolinium likes to eat up neutrons for our IBD reaction, surrounded by a layer of just liquid scintillator. And the reason for this is that for those events occurring near the edges, we want to be able to measure their energy just as well, or close to just as well, as we measure the energy of an event occurring near the center. And then finally, the last layer is mineral oil, which provides additional shielding because we need to suppress backgrounds. There's radioactivity coming from the stainless steel, from the PMT glass, etc. And then these detectors, they're super sensitive. We put them in water or in some shield of liquid scintillators, some kind of liquid shield, basically, because that way you can tag muons, veto muons from cosmic rays, and you can also shield your detector even more against natural reactivity and neutrons from cosmic rays. And Yes, as I already mentioned, we use gadolinium in the scintillator to be able to enhance our capture signal from the IDDs. That's one type of experiment from our modern era. There's another category which we're going to call SBL, short baseline experiments. And these experiments basically just appeared and disappeared. They're almost all of them done now in less than a decade, because they're much smaller scale. And the motivation, or the main motivation for them, was to search for sterile neutrinos at very short baselines. Why, you may ask? Were these experiments interested in looking for sterile neutrinos at short baselines? That's an excellent question, and I will answer that later. For now, just let me just tell you, there is a good reason. There was a hint that perhaps there were sterile neutrinos in this energy region, and so all these experiments jumped on the opportunity to perhaps be the first ones to discover that. And so 2 of them use LEU reactors, 4 of them use mostly HEU reactors. Why? Because you need to be at short baselines, and perhaps only in Russia you can get so close to a nuclear reactor. In other places it's very difficult. And so if you want to get meters from a reactor, it's a lot easier if you go to one of these smaller research reactors. And so I'm not going to go into the details. They use basically scintillator, either plastic or liquid. They dope their scintillator with different elements, lithium or gadolinium, typically. But what's most important to remember here is that most of these experiments, with only one exception, which is NEOS, they use segmented detectors. And what this means is that you have different regions of your detector that are optically decoupled from each other. In other words, you can make the measurement of the energy spectrum for independently at different regions of your detector. And there's a very good reason for this. The reason is that these experiments, they're looking for a distortion caused by oscillation in the energy spectrum. And this distortion, the smoking gun, is that it should change as you change the baseline. And so since the oscillation length here is comparable to the size of the detector, you can look for this change within the detector. So it's another way of making a relative measurement to cancel out the uncertainties from the reactor prediction models. It's just not a relative measurement between detectors. It's a relative measurement between cells in the detector. Okay. So this is why they're built this way. Now, what are some of the results that have come out of these experiments? Let me show you a couple of highlights. I'm not going to show you every result because it would take forever, but let me show you Diabe. We just released this result in Neutrino 2022. So this was at the end of May. And these are our latest and greatest oscillation results. And so this is the data in the far hull, which is where we expect to see our strongest oscillation signal. And basically what this is showing you is that this is the energy spectrum. Remember, it's this thing that peaks at around 3 MeVs. We already explained why it looks the way it does. And if there were no oscillations, our near detectors tell us we should be seeing this blue spectrum, but that's not what we see. We see less. And this deficit is bigger here as opposed to, for example, here. If I take the ratio of the data over the expectation in the case of an oscillation, it looks something like this. And it turns out this is exactly what you expect from the 3 neutrino framework of oscillations. It's a clear-cut smoking gun signature of neutrino oscillations. And you can see that we can map it out pretty precisely. So from this distortion, we can actually extract remember what I said about the amplitude of the effect is the mixing angle. The energy dependence of the effect gives us information about the differences in the squares of the masses. So we can extract both of these parameters at the same time. And we've done a very precise measurement of these 2 quantities. So for Theta 1.3, we have the best measurement in the world, and that was better than 3% precision. And for delta M squared 3.2, so we have a nice measurement, 2.3% precision. And the interesting thing, well, a couple of things here to notice is these are other experiments. We're all pretty much consistent within 1 or at the most 2 sigma, which is really good. And it's particularly noteworthy given the fact that some of these experiments, for example, T2K, NOVA, instead of using MEV neutrinos, they use GeV neutrinos. Instead of using 2-kilometer baselines, they use hundreds of kilometers of baseline. So it's a strong test of this neutrino oscillation framework. It holds up. It works for hundreds of kilometers. It works for 2 kilometers. It works for GeVs. It works for MEVs. It works for mu neutrinos, just as it works for electron antineutrinos. It holds up. So that's one of the conclusions to get out of here. And the other one is that, yeah, we have similar precision for this delta M squared as some of these accelerator experiments like T2K. That's just a highlight of the kind of oscillators coming out of Theta 1-3 experiments. Now, what about the short baseline experiments? I show you the results from Prospect here, again, as an example, because we don't have time to cover all of the results. Remember the philosophy here. The philosophy is looking at the spectrum and seeing if we see a distortion that depends on baseline. And so here you see the spectrum. It looks consistent to the one in the next baseline, looks consistent with the one in the next baseline. You get the idea. So no signal for sterile neutrino mixing, unfortunately. And so what we can do is we can just put some limits. Now the limits are in a region of parameter space that is typically for delta M squared 4-1, it's from, let's say, 1 EV. Just remember 1 EV squared. Just keep this in the back of your head, because if you have an experiment with a longer baseline, then you can cover smaller regions of delta M squared. I will come back to this in a second. Now, I do have to let you know, in case you didn't already, that there is a positive claim, or a claim for a positive observation, positive signal for sterile neutrino. It's coming out from one of these 6 experiments, which is called neutrino 4. And they claim that they see this signal, which, since this is L over E, it's a clear-cut oscillation signal. And when they translate this to this same parameter space, then they say this is the parameter space where our signal says that there's a sterile neutrino. Now, this is heavily disputed, and we don't have time to go into the details, but there's some concerns about the significance. There are concerns about the efficiency of the different cells. There's also concern about the energy resolution and how perhaps it may not be properly taken into account. So then there's another problem, which is that this region of parameter space is pretty much excluded by Prospect and by the other experiments. So it's in conflict with the non-observation in the other experiments. Even so, when you include this positive signal with the other experiments and you try to make a global fit, you get a limit. It gets kind of washed out because the non-observation ones just overwhelm it. And so this is basically the state of the art of where we are in searching for sterile neutrinos with reactors. These limits are the ones from the SBL experiments. This here in green are the limits from Diab-Bay and Bouget 3, again, reactor experiments, but Diab-Bay, remember, the baseline is much longer, kilometers instead of meters. And so we can cover a lower region of delta M squared. We can cover a wider amount of space here in delta M squared, 4-1. And this region here is the region of space motivated by an anomaly that is called the reactor antineutrino anomaly, which is what basically caused all of these experiments to pop into existence. And I will describe that next. So let's talk about anomalies very briefly. And by anomalies, I mean these data versus model comparisons that don't agree. That's what an anomaly is, at least in this context. So what we can do, in addition to doing oscillation measurements with reactor antineutrino experiments, is we can compare what we're getting out of the nuclear reactor compared to what we expected to come out of the nuclear reactor. Why do we care about this, you may wonder? And there's several reasons why it's actually pretty important. It's important because, okay, experiments like Diab-Bay, you have to pay more and you have near detectors and far detectors that cancel out these effects, but maybe we don't want this. If we can fine-tune the models such that they work really reliably, then we don't need the near detectors. And so, for example, for future experiments, if we can get these models to work well, good enough, precisely enough, then we save money, we save time, we save all kinds of resources. It's also important to understand these models and to get them benchmarked and to build confidence in them, because one of the possible applications of neutrinos you might have heard of is that they can be used to monitor nuclear reactors. And so you need to understand what's happening there if you're going to do this monitoring, or else you're not going to be able to interpret your results. And finally, you can use neutrino spectra and neutrino measurements in general to benchmark nuclear databases, because nuclear databases, you can use all that information to predict what the neutrino spectra should look like. And if they don't agree, it means there's something wrong with the nuclear database. And depending on where the disagreement is and all of that, you can perhaps identify where the problem is. So it's a good test of nuclear data. Now, when it comes to predicting what comes out of a nuclear reactor, there's two methods. One is called the ab initio method. And here, basically, what you do is you go from the bottom up. So you have your nuclear databases, you know, when you fission uranium-235, you have this probability of producing krypton versus this probability of producing xenon, whatever. And then you, from the nuclear databases, you know what the beta decays for xenon and for krypton and for all of these things are, and for all of their daughters are. And so you can basically sum of these thousands of branches and you predict the neutrino spectrum. This is one way. The other way is you can measure the beta spectrum from the fission of uranium and plutonium. This was done in the 80s in a reactor called ILL in Grenoble in France. So these are very old measurements of the beta, so the electron that comes out from the fission and then from the decay of all the products. And then you can convert from electron to antineutrino. And you do this conversion by fitting with a bunch of virtual branches. That's what it's illustrated here. This method is believed to have smaller uncertainties, but it works worse, as I will show you in a second. It's one of those ironies of life. The latest implementation, or the state-of-the-art conversion method, is the so-called Huber-Mueller method that many of you, I assume, have already heard about. So the first thing you can do is, let's just look at the rate. And by total rate, or rate, I just mean the total yield. Yield is another, pretty much I'm going to use it as a synonym of rate. So it's the time average yield, how many neutrinos per fission we see from all the isotopes combined, from the sum of all four. And we can compare that with the expectation. And this is the so-called reactor antineutrino anomaly, that this comparison has been done, and it always comes short. We detect less neutrinos than we expect by about 5 to 6%. And it's a pretty significant effect. It's become even more significant recently because we've added new measurements. The most precise measurements nowadays come from double show, Bouget 4, and Diabet. These measurements are hard because you need to know like the absolute efficiency of your detector, things like that. But we've managed to go below 2% in precision. And so what could be causing this? Well, it could be that all of the experiments made the same mistake. Unlikely. I would say impossible, essentially. It could be, as represented here, that there's a sterile neutrino. And so it's a sterile neutrino with high mass. Therefore, the oscillations are very quick. And so that means that you don't see the oscillations, you see a deficit, because you don't have the resolution to resolve all those oscillations. You just see a constant deficit. And maybe that's what's happening here. This is the most exciting possibility. Maybe. That would be great. But it's unlikely, as I will show you. And it's possible, and this is the most likely option, that there's just problems with the predictions. And so new data has come to light recently with these experiments, the Theta 1-3 experiments and the SBL experiments. And one of the things we can do with these experiments is compare not just the rate, but the shape. And when we do this comparison of the shape, what we measure versus what we expected from, for example, the Huber-Mueller model, which is a conversion model, or one of the summation models, which is this SM 2018, we see that they both don't agree. Well, I mean, I guess everything's relative, right? It agrees pretty well if you look at it from this perspective. But if you zoom in, you see that there's this bump, which here looks like a bump, here looks like a deficit, because this is data over Monte Carlo, this is Monte Carlo over data, but in both cases, it's the same bump, okay? And so yeah, it agrees pretty well, but there's this annoying bump. And the bump is found for both types of predictions. Interesting. So this already tells you, this cannot be explained by sterile neutrinos because it's just a bump at one fixed energy. And so it already tells you, since it looks like there's problems with the prediction here with the shape for sure, then probably there's problems with the prediction for the rate as well. And maybe there's no sterile neutrino. More information has come to light because the question you can ask is, okay, there's 4 isotopes that contribute to the total flux. Maybe one of them is the culprit. And it turns out that an experiment like Diabeo and Reno, even though we get the combined, in the aggregate flux from the 4 isotopes, we can disentangle the contributions of the 2 most important ones by looking at how the flux evolves as a function of fission fraction. And what's happening here is that the number of neutrinos per fission that you get when you fission plutonium is smaller than the number of neutrinos per fission that you get when you fission uranium. And so as you burn your fuel in your reactor, you get less neutrinos. And from fitting these data, you can extract how many neutrinos per fission are coming out of uranium versus how many are coming out of plutonium. And you can do this as a function of energy, or you can do it in total. And this is the punchline. That's why I put this in red. For plutonium, we find good agreement between the model and our measurement. Plutonium looks okay. Uranium, which is the x-axis, there's a big discrepancy. So our measurement is here, the model is here. So it looks like this guy, uranium, is the primary culprit of the reactor antineutrino anomaly. And this in turn weakens the sterile neutrino hypothesis, because if these really were sterile neutrinos, then the deficit should appear from both plutonium and uranium and all kinds of neutrinos, doesn't matter how they fissioned. But here we're seeing a deficit that is attributed to only one isotope. And so it weakens the sterile neutrino interpretation. Now, the other thing important to conclude here is that you see a bump in both uranium and plutonium. So that seems to not be unique to just uranium. We can blame uranium for the rate anomaly, but not for the shape anomaly. In other words, we get a consistent story from HEU experiments. And let me not get into detail because I just realized I have like 10 minutes left, but consistent story. And then the other important piece of evidence here is that there's just been, in the last 2 years or so, a new measurement. Remember, I mentioned these measurements done in ILL. There's a new similar measurement done in Russia in the Kurchatov Institute. I'm sorry if I pronounced that incorrectly. And they didn't do everything that was done at ILL, but they just looked at the ratio between uranium and plutonium, what they observed versus what was observed in France in the 80s. And they see good agreement in terms of the shape, but they see like a constant deficit. And guess how much deficit that is? It's 5%. It's the size of the reactor antineutrino anomaly. So the conclusion is that, and this is what this complicated plot is meant to illustrate. Here, where we are at, these are the fluxes of uranium and from plutonium. Compare what is measured versus what is expected. And this here is what the conversion methods predict. These ellipses are what the data tell us. And this is what the summation method tells us. And this is what this new measurement done in Russia tells us. So everything except the conversion methods agree. Everything is here. It seems like the answer is here. Plutonium, we're pretty close to 1. We are modeling that one well. Uranium, we're closer to 0.94, 0.95, somewhere around there. We got it wrong by 5%. And so it means that we basically need to fix our models, and we cannot just fix the model. We need basically to new measurements, to redo those measurements in ILL and get them right. So is there a sterile neutrino here? It looks, there's still room for it, but the hypothesis is weakened. It looks like it's just nuclear physics. We got wrong the uranium flux. Okay, So very quickly, what do we expect in our field for the future? There's this new experiment called Jianmen Underground Neutrino Observatory that's going to come online very soon. This is next generation reactor neutrino experiment. A thing of beauty, in my humble opinion, a massive detector, 20 kilotons of liquid scintillator at 50 kilometers from 8 nuclear reactors, again in China, because if you want to be close to so many reactors, to my knowledge, there's only one place in the world where you can do that, and it's in China. And so this is a massive detector, again, reactor neutrino experiment, but it's going to have one very important distinctive, which is that it's going to have a beautiful energy resolution of 3%, whereas the detector like Diabei had closer to 8%. And I'll explain why this must be the case in a minute. But first, let me just impress on you how difficult it is to build a detector, a liquid scintillator detector that has a resolution of 3% at 1 MeV. Basically, you might think, okay, so we need to see more photons, right, to get a better energy resolution. How do we increase the number of photons? Well, let's just put more PMTs in there, sure. But it turns out, since PMTs are round, you can only put so many close to each other. Basically, in the order of 75% of the inner surface, you can cover it with PMTs, but that's as high as you can go. So this will only buy you a factor of 2 times more light compared to what you need. You need a factor of 5 times more light compared to what is typically seen in these kinds of experiments. So you also need a better liquid scintillator that shines more and that is more transparent. And you also need better sensors, better PMTs. PMTs that have basically double the efficiency than the predecessors. And in Juno, we claim that we've put all of these together into one experiment. So it's really pushing the limits of this kind of technology. Now, in order to have a good energy resolution, you also need to watch out for any residual effects after calibration. And so we have this approach where we have big PMTs and small PMTs in the middle. And this is because the small PMTs allow us to calibrate the big ones. And they also bring additional benefits on the table. And so I don't have time to go into the details, but I do want to highlight that the small PMT system of Juno is a place where Saphir has been very heavily involved. We still have, to this date, an engineer in Saphir who helps us very much with the small PMT of Juno. Now, why do we need such a good energy resolution? Here's the answer. It's because we want to image these oscillations. You see these little wiggles, we need to be able to see them so that we can measure all of these oscillation parameters, and also so that we can tell the difference between the red and the blue. And by telling the difference between the red and the blue, we can distinguish what is the right ordering of reactor antineutrinos, of neutrinos in general. So this is why. Now, Juno is also going to do a bunch of other things that I won't go into details, but he's going to do supernova neutrinos, solar neutrinos, geoneutrinos, proton decay, and a bunch of other things. So there's a very rich program there ahead. And let me just finish with this, which is that the experiment is coming online soon. The construction is progressing full speed ahead despite COVID. This is how it looks like right now. So we already have this stainless steel sphere built. The acrylic that goes inside, so it's a sphere inside a sphere, basically. So the inner sphere of acrylic that's going to hold the liquid scintillator is being built. Basically, 3 layers are already in place. And we have a lot of PMTs ready, potted. The scintillator is getting ready, and we expect to finish construction by 2023. So, oh yeah, sorry, I forgot one more quick thing. Juno's going to have a satellite detector. And with this satellite detector is also going to have a beautiful energy resolution. And we're going to be able to see the fine structure in the reactor antineutrino spectrum. Because this spectrum comes from a bunch of beta decays, remember? And so we expect, since these are all these nuclear effects, we expect to see these sharp edges. And with this satellite detector called Tau of Juno, we're going to be able to see that for the first time. There's also another proposal on the table that would allow us to measure the uranium-235 spectrum more precisely than we already know it. It's called Prospect 2. It's the follow-up to Prospect 1 that I briefly talked about. Okay, so let me stop here. Here's the summary. Nuclear reactors, I think they're fantastic neutrino sources. They're intense, available, etc. You remember the list, right? There's been cutting edge physics that have been done with reactor experiments and continue to be done. For example, leading precision of measurements for neutrino oscillation parameters, among other things. And the field is going to continue to grow, it looks like, because Juno is this massive experiment that's going to come online very soon, and it's going to do a bunch of things. And as I mentioned, I deliberately decided not to cover that here. There's a whole new program of looking at what comes out of a nuclear reactor using a different reaction, not the IBD one, but the coherent elastic neutrino nucleon scattering, which is sevens. So let me stop here. Thank you very much.
Thanks, Pedro, a lot for this very nice talk. Is there's any question, please raise your hand. Francisca, please.
Well, no, I was just clapping my hands to say thank you to Juan Pedro. But in the meantime, it's just curiosity. You mentioned the stellar neutrino experiments, that they appear somehow rapidly. Are they now, they already have taken data, I understood, and now they are not doing any more data taking, or what is going on with that in the future?
Yeah, so it's a good question. Most of them are already done. Oops, yeah, here. Most of them are done. So there will be upgrades to some of them. DANS is gonna be upgraded. Prospect hopes to be upgraded. So it will be this Prospect 2 that is mentioned. NEOS 2 just released data. So this one just is brand new. And then Solid, we're still waiting for their first results. But for the others, basically, for all of them, we've already had, except for Solid, we've already had a first round of results. And so in some cases, there will be upgrades, in others, no. But we don't expect the picture to change significantly. At least that would be my naive expectation. We will refine some of these measurements, but I don't expect any big surprises there. I hope I'm wrong, of course. I hope I'm wrong. Yeah.
Thank you.
Giovanna, please go ahead.
Pedro, one question. So concerning the reactor neutrino anomaly, when you say your model's prediction, you mentioned two, the H&M, I remember, HM and SM. So
HM?
these models basically, just correct me if I'm wrong, but they predict, I mean, the idea is to predict the cross-section per fission.
Yes, that's another word for yield. Yes.
Okay. So yeah, maybe, so okay. That's another word for yield, true. So when you, I mean, basically, if you have several tunes to this prediction, so basically theoretical uncertainties can help. I mean, if you have several models, I'm thinking, can they give you something to say, maybe perhaps reduce the, so this graph that you show when you have the S model in blue, I don't remember which slide, perhaps the next one. You are comparing both models there, but in the global picture. I mean, I'm interested if this could be, I mean, if basically plugging in new models in that plot will help you somehow basically rule out the stellar neutrino hypothesis.
So I think the stellar neutrino hypothesis, at least in the region where we expected it from the reactor antineutrino anomaly, is almost ruled out, even if, I mean, despite the uncertainties of the models. And this is because we use these experiments that use this relative measurement, like Prospect, right? Or that uses the relative measurement between cells, and you don't see anything. And so I think that's the most powerful evidence that there is no stellar neutrino, at least in the region that those experiments are sensitive to. Now, you were wondering if adding more models would help, and perhaps a little bit, but the thing is, all the summation models pretty much end up around here. All the conversion models pretty much end up around here. Why? Because they start from the same data. The conversion models start from these measurements from ILL, these old 80s measurements that I'm arguing should be redone. And all the summation models start from, okay, there are several nuclear databases, but not so many, NDEF and et cetera. So that's why the models don't change that much. What changes more is the family. And so either conversion, you end up here, summation, you end up here. I don't know if that helps.
Okay, but maybe I can ask, okay, I think I'm confused now, because how do you know from this plot that there is the possibility of a straight neutrino?
From this plot, no, because this plot, since now we broke it down by plutonium and uranium, this plot suggests that the problem is not in plutonium, the problem is only in uranium. And so it doesn't tell
because you see
that
the
there's a
pool,
neutrino.
the pool of the global feed, okay, of the integrated, this red thing.
Yeah,
right?
so
Okay.
the suggestion for the sterile neutrino comes when you don't worry about where the neutrinos come from, uranium or plutonium. You just look at the integrated flux compared with the integrated prediction, and you see this deficit. But
Thank you. I understand.
Now we know that it's one isotope that is most likely the culprit. And so it looks like it's just nuclear physics, it's not new physics. Yeah. I hope
see.
that helps.
Yes, thanks. It helps. Thank you.
Yeah.
Sergey? You have
Yeah,
a question?
okay, yeah. Okay, Pedro, thank you very much for this very nice, excellent talk. Look, you didn't mention the LSND and mini-Boon anomalies. What is the status of these anomalies, which at least were typically interpreted as sterile neutrino?
Yeah, so I actually had some slides and I decided to remove them because I knew I was going to be close in time. But it's a great question. I'm happy to tell you. So I guess two things. Oh, and I think that I do have a slide. I think I put it in the back in a second. Yeah, so I did have a slide here that, as I said, it was going to be in the talk and I removed it. With Diabé and Bouget and Minos, you can combine all those experiments and place some constraints on the parameter space or the mixing angle that would be the one driving the anomalies from the mini-Boon and LSND experiments. And basically these anomalies are here, as you can see. So it's basically the shaded regions. And our limits are in red. And you can see that we say no. What this is telling you is, let me put it in words, maybe it's simpler. LSND and mini-Boon claim they see something which they attribute to sterile neutrino. We say, if what you're seeing indeed is a sterile neutrino, we should see something, but we don't see anything. And so we actually exclude this region of parameter space. In other words, their anomaly cannot just be explained by sterile neutrinos, at least according to us. That's one thing. The other thing is that the micro-Boon results just came out. And I don't have a slide for those because that's accelerator neutrinos, but the micro-Boon results came out and said, we don't see an excess of electron neutrinos. Not only that, but we don't see an excess of photons either. So in other words, we have no idea what the heck happened with mini-Boon and LSND because it looks like it's not a neutrino axis. And it looks like it's not an obvious photon background. So it could be some other background, or at this moment, people are retreating into these even more exotic scenarios because the pure vanilla sterile neutrino just won't cut it. It doesn't fit with the data. So just sterile neutrino doesn't do it. You need more sophisticated, even more exotic physics, or some other background that nobody has thought of yet. So we need more data. We need micro-Boon to analyze some of those exotic scenarios. And we need to also we also need micro-Boon. Micro-Boon is really the one who's going to be able to test many of these things. We need micro-Boon to also look for some other backgrounds that could look like electron neutrinos in LSND and in mini-Boon.
Yeah.
I hope that that answered your question. So it's a complex.
Yes.
It's a very complex situation, and things got even weirder now because we just really what is it? There's no obvious candidate.
Yeah, but at least vanilla scenario, scenario for sterile neutrino is excluded. Yeah.
The
Right.
sterile neutrino only scenario,
Only, yes.
I think is fair to say,
Yeah. Mhm.
is very unlikely.
Mhm.
Exactly.
Okay, thank you. Yeah.
Sebastián Olivares, please.
Hi, Pedro. Yes, I was going to ask you kind of like the same question. So let me try to do like a different one. So when you talk about this like access on microbone and millibone, all the time, like it happens in neutrino experiments, also happens in nuclear physics. You're talking the excess of like less than 3 sigma. How you compare that with what people from collider physics we expect that when we have something of 3 sigma, we don't care too much unless it's a little bit more than that. So if you can explain us
So
that.
I believe you're asking my opinion. Basically, should we put so much attention on 3 sigma anomalies, right? I don't know if that's exactly, I don't know if I paraphrased your question.
Yeah, I mean, it should be a reason. I'm not saying that you should not, but I'm just asking like the reason.
No, it's a fair point. I mean, there's been throughout history a lot more 3 sigma anomalies than you would expect, just from the fact that it's 3 sigma, right? And many of them have not panned out, but some have. So in this particular case of mini-boon and LSND, however, I should point out that the combined significance, if you combine mini-boon and LSND, it's actually more than 5 sigma. And so I guess that leads me to say that even if it's 5 sigma, it can still be bogus, right? It can still be just something that we don't understand rather than something really new. So I'm not sure how to answer your question. I would say, of course, more significance is better. Even that is not a guarantee, because you could have just done something wrong, not on purpose, of course. It could be just a background you didn't know, a systematic effect you didn't know, etc. And we should, whenever an anomaly like this occurs, I think the right thing is to go and investigate it. The problem is that this anomaly has just been impossible to remove. I hope we will resolve it soon, because it draws all these resources and time. And it's been doing so for decades. I don't know, Sebastian, if that was more or less what you were getting at, or if I just went on a tangent.
No. I mean, like, it's okay. But many times you have these 3 sigma differences, and I understand that the experience are much different between colliders and what you have here. The same thing that happened, for example, in LHCb and all these other experiments, which are very important. And another question, just to not keep in this, is that when you talk about this anomaly between the models, all these neutrino, sterile neutrino, you know how they calculate those Monte Carlo? They're truly based like Monte Carlo theoretically, or they have also like a data, so a data characteristic, so they're doing also with real data.
Sorry, when you say which Monte Carlo are you referring to?
You were talking of 2 Monte Carlos that I forgot the name. The one that
the conversion
that also,
and these ones.
Yeah, those ones, the HM and the ILL. So those 2 Monte Carlos are calculated purely on like theoretically Monte Carlo base, or they also have like a data fit in the middle?
Both of these begin from data. So this one uses, basically just combines all the data in nuclear databases from the bottom up, but it's data. The problem is that there are places where we don't have data, and so they have to make some assumptions, but it's mostly data. And then for the other one, the starting point is this beta spectra measured in Grenoble in France in the 80s. And then it's massaged so that it's transformed from beta to neutrino. But in both cases, the starting point is data. I don't know if that answers your question. So then they're compared. Sorry.
Yeah, it answered, but what is like kind of like strange is that beside the yield that is different, you also have the shape that is different. So
Yeah,
I
it's
thought
very
maybe it
strange.
should be related with something like that.
So a few of us think that it's got to be something common to both. So since both fail in the spectral prediction, it's got to be something common to both, such as some of these branches, because both of them use these branches, these beta decay branches, to make the prediction of the spectrum, and maybe some of those are just wrong, and that's why we're getting the same mistake with both predictions. So it's got to be something common to both.
Thank you, Pedro.
I hope I answered your question. If not, let me know.
Yeah, you did.
Giovanna, you have a question, or just your hand is raised from the previous?
I have another question about the mini moon and the other anomalies, since you showed the plots. Can you exclude the mass of the vanilla sterile neutrino framework? I mean, can you say we are excluding a sterile neutrino with certain mass from those plots? Because if this picture is ruled out,
with a mass splitting. Yes.
because the exclusion it's on the mass difference as a function of angle.
Yes.
So I mean this is not excluding, let's say, a TeV scale sterile neutrino, right?
Because we don't know the absolute scale of neutrinos. So you would have to use additional data there, maybe from cosmology or something else, to make that
Right.
exclusion. Also, if the mixing angle is small, in other words, if these sterile neutrinos couple very lightly to the active ones, then we cannot say anything. And so it could be that there's a neutrino here. It's just since it couples so lightly, we cannot exclude that. So no, we cannot exclude, we cannot say anything categorical about the masses of the sterile neutrino.
Okay, good.
All we can say is we exclude the LSND and mini bone region. Yeah.
So we are safe for Carlos.
Okay, thank you. Can I make a stupid question related to what Sebastian was asking? At the LHC or Collider, you have many more analysis, right? So experimental analysis. So the probability of having a 3 sigma excess due to a statistic should be greater, right? Or no? Just by a probability effect, if you have many more analyses, it might be that one of them you have an excess due to statistics in compared with the neutrino experiments. Is that right, what I'm saying? It's a question for the experimentalist.
So I can give you my humble opinion. I would say no. So because 3 sigma means the confidence that you put, how unlikely it is for a certain spectrum or result in general observation to be consistent with the null hypothesis, right? And so as long as you take into account all the systematics and all the errors in general properly, then you should be able to quantify your significance properly, and therefore you should get in average the same number of 3 sigma results as in any other field, right? As long as these things are done properly. And actually, I would say that in neutrino experiments, we now also have, excuse me, a lot of analyses. We have for example, our diabase results, we have like 4 independent analyses. And it's just, we select one for the paper, but we have multiple groups working in parallel, precisely to avoid biasing ourselves. You know,
okay, thank you.
Because we cross-check ourselves. We don't want to be the next anomaly. Maybe some experiments like being the anomaly, but we don't want to.
Okay, thanks. So is there any other question? So if not, thank you again for this very interesting talk, and thank you all for attending these seminars, and see you at the next Saphir webinar next month in October.
Thank you for the invitation. It was really nice to see you all virtually.
Thank you.
Thank you, Juan Pedro.
Thank you.
Pedro.
Thank you.
Bye
Thank you
bye.
all.
Bye.
Thank you
Ciao.
all. Bye.